Hello, I am Professor Nagnath Hulle from GH Raisoni Institute of Engineering and Technology. In this video, we will try to understand the two basic rules, that is Kirchhoff's current law, KCL, and the Kirchhoff's voltage law. To begin with, the statement, algebraic summation of currents at any junction is 0. Now first, in this particular statement, we have to understand the meaning of junction. What do you mean by the junction? Now here, if we have one resistor here and this is second resistance, in this particular case, this common point is not a junction or not a node. If we have 3 branches, minimum 3 branches or more than 3 branches, then that particular point is known as a node point or junction point. For understanding this particular law, we have considered the node point having 5 branches, 1, 2, 3, 4 and 5, and in this case 3 currents I1, I2, I3 are the incomings and I4 and I5 are outgoing currents. Now here the statement indicates algebraic summation with sign, summation with polarity. Now what should be the sign or what should be the polarity? There is no standard sign convention. Here, for any resistor, if you are taking the, for any junction, if you are taking the incoming current as a positive, then we have to take the outgoing current as a negative. Or if we are taking the incoming current as a negative, then we have to take the outgoing current as a positive. This is outgoing current I am assuming. Now here in this case, what I will assume? I will assume the incoming current as a positive and outgoing current as a negative. Using these sign conventions, we will explain this particular statement. Now here in this case, if I am applying the KCL at this node A, or I will call it as node A, in this case incoming current, algebraic summation of the currents at any junction is 0. Here in this case incoming current is I1, it is a positive, incoming current I2, it is positive, incoming current I3, it is a positive, then minus I4 because it is outgoing, minus I5 because it is again outgoing, which is equal to 0. This is the applying the KCL at any node. If we are simplifying it further, that is I1 plus I2 plus I3, which is equal to, that is I4 plus I5. Now here look at the second statement. Second statement itself indicates the second rule, or it's a or. In this case incoming currents toward the junction is equal to the outgoing current from the junction. This here, these are the incoming currents is equal to these are the outgoing current from the junction. This indirectly the summation of all incoming currents is equal to the summation of all outgoing currents. This is the statement of the KCL or Kirchhoff's current law. Now here I will take the simple sum or simple problem based on this particular law, that is Kirchhoff's current law. Now here in this case, before starting to apply the KCL at any complicated network, we have to first mark the nodes or junctions. What is a junction? I discussed previously. Junction is a point at which 3 or more than 3 branches meet together. Here we have the two junctions, the junction A and junction B, or node A and node B. If we are applying the KCL at node A, in this case KCL at node A, here in this case incoming currents is equal to outgoing currents is the statement. Incoming currents are 3 plus 8, these are the incoming currents, and 5 plus I1, these are the outgoing currents. From this we can find out the value of the current I1, which is equal to, that is 3 plus 8 minus 5, which is equal to, that is 6 amperes. 6 amperes is the current I1. And here in this case, if we know the value of the current I1, we can apply the KCL at the second node, that is node B, and we can find out its value. Now if we are applying the KCL at node B, that is second node, in this case again the statement remains the same, that is incoming currents is equal to outgoing currents. Now here for the node B, incoming current is I1 7 ampere and outgoing currents are I2 and 1 ampere. Now here in this particular case, that is incoming current I1 plus 7 amperes is equal to outgoing currents, which is 1 ampere plus I2. We can substitute the value of the I1, which is 6 plus 7, which is equal to 1 plus it is I2, and from this we can find out the value of the I2, which is equal to 6 plus 7 minus 1, and which is equal to the 12 amperes. Now here in this way we can find out the values of the currents I1 and I2, and this is the one of the way to solve the sums based on the Kirchhoff's current law, that is the KCL. Now I will start with another statement or another theorem or another law, which is the Kirchhoff's voltage law, that is the KVL. Now here it states that the algebraic summation of the EMFs and potential drops in any closed circuit is 0. Now first here, algebraic summation means summation with sign, summation with polarities. Of what? EMFs. EMFs are nothing but the applied voltages. Here applied voltage is V. And potential drops. Potential drops are nothing but voltages developed across R1, R2 and R3. The voltage developed across R1 will be its current into its resistance, its current into its resistance, its current into its resistance, and so on. Means before applying the KVL to any of the circuit, we have to assume the suitable direction of the current, or we have to select the current. Here in this case I am assuming the direction of the current as a clockwise, and I am naming this current as I. Now here, while applying the KVL, here there are the sign conventions. Algebraic summation means we have to find out the polarity of the potential. Here some tricks are there to find out the polarity of the potentials, and we will follow one of them. Here in this case, if it is a resistance and current is flowing in the forward direction and we are traveling with the direction of the current, in that particular case that potential drop is taken as negative. And here if we are traveling opposite to that of the direction of the current, in that particular case potential drop is taken as a positive. But when we are applying the KVL to the complicated network, this becomes complexity or some difficulty. That's why I am using this simple technique, in which here, if this is the direction of the current always flow from the higher density to lower, is this terminal acts as a positive, this terminal acts as a negative. And in this case, move with the direction of the current, positive to negative, we will get the negative potential drop. And if we are traveling with the opposite to that of the direction of the current, in that particular case, negative to positive, we will get the positive potential. That's why I will use these sign conventions in this particular case. Now, mark the polarities depending on the assumed direction of the current. Here, for this assumed direction is clockwise, that's why current in the resistor R1 will be the forward, that's why it will be plus, this is minus. For the resistor R2, it is current is flowing in the downward direction, that's why it will be the plus and minus. For the resistance R3, the current is backward, that's why it will be the plus and this sign will be the minus. If we have taken this current direction as anti-clockwise, in that particular case, this will be the plus sign, this will be the minus, this will be the plus, this will be the minus, this will be the plus, and this will be the minus, and accordingly we are in a position to apply the KVL for that particular case. But here in this case, I have taken the direction of the current as a clockwise, and accordingly I have marked the polarities. Now we will apply the KVL and we will start from this particular corner and we are moving in the loop. If I am traveling in this clockwise direction, we can travel in the anti-clockwise direction also, but here negative to positive, its EMF or its voltage will be the plus V. Then we are traveling from positive to negative, that is minus. Its potential will be its current into its resistance. Its current is I and its resistance is R1. That's why its potential drop will be the I into R1. Then positive to negative for the R2, which is minus. Its current is I, its resistance will be the R2. Similarly for the resistor R3, here positive to negative minus, which is minus, its current is I and its resistance is R3, which is equal to 0. This is the method to apply the KVL or Kirchhoff's voltage law. If we are simplifying further, V minus I is taken as a common, then it will be R1 plus R2 plus it is R3, which is equal to 0. If we are simplifying further, this V is equal to I into it is R1 plus it is R2 plus it is R3, and by this way we are in a position to find out the values of any of the unknown. It may be V, it may be I, or it may be the resistance in this particular case. I will take one of the simple problem based on this calculation of the current or maybe the resistor. Here in this particular case, calculate the value of the resistance R. And here is the resistance R. We are planning to calculate its value by using the basic laws, that is KVL and KCL. Here, before applying the KVL, we have to find out the current in each branch, current in all branches, or at least we should know the direction of the current in each branch. Now here, we will plan accordingly. The 20 ohm of this resistance has a voltage of 60 volt across it, and its polarities are given. This is a plus and this is minus. This direction of the current will be something like this. I will name this current as I20. This is incoming, this is incoming. This current will be the outgoing. This current I will name it as a I10 and it is outgoing. We can assume the reverse direction also. In that particular case, answer is coming to be negative. Again, no issues. This current, it is not necessary to assume it as outgoing. We can assume it is also as incoming. In that particular case, answer will be the negative. That negative sign shows itself. Assumed direction is a reverse as that of the original direction, but it is not the wrong current. Now here it is incoming, this is outgoing, means it is something like this. I will assume this current as a downward. I will name this current as a IR, that is current in resistor R. Now here first to calculate the current, because we are planning to calculate the value of the resistor R, that's why we have to apply the KCL at the two junctions. I will name this junction as A and this junction as a B. First we will calculate the currents in this particular case. If we are applying the KCL at node A, in this particular case, incoming currents is equal to outgoing currents, that is 6 amperes plus I20, which is equal to I10. Here, two unknowns are there, I20 and I10. First, I will find out the I20. This I20 is equal to current in this 20 ohm resistance, voltage across that resistor divided by its resistance, which is equal to 60 divided by 20 is 3 amperes. Is here, in this case, the current I20 is a 3 amperes. Now it is 6 plus 3, which is equal to I10. Now here, the value of the current I10, which is equal to 9 amperes in this particular case. Now here, we know the current I10 as well as current in 20 ohm resistance. Now, this current is already known, 4 ampere. Now we will plan to calculate the current in resistor IR. For that we will apply the KCL at node B. And if we are applying the KCL at node B, incoming currents is equal to outgoing currents again. The KCL is the same. That is I10 is equal to IR plus 4 amperes plus it is 2 amperes. And here, if we are planning to calculate I10, which is 9 amperes minus 4 amperes minus 2 amperes, which is equal to 3 amperes. Now look at current in this branch is a 3 ampere. In this resistor is 20 ohm resistor is a 3 amperes, and current here in this case is also 3 amperes because this is one branch. What is the definition of the branch? Branch is nothing but path between any two nodes. Now here, if we are applying the KVL now, for this particular case, if we are applying the KVL to calculate the value of the resistor R, we are traveling from this point, we are traveling in the upward direction. First we will mark the polarities. Its polarities are marked. It is forward, that's why it will be the plus, and this is minus. It is downward, that's why it will be the plus and minus. If we are traveling from this particular point, positive to negative, which is minus, its resistance is 20 and its current is 3. Then positive to negative, which is minus, the resistance is 10 and value of the current I10 is 9 amperes, that is 10 into 9. Then again positive to negative, which is minus, its current is 3 amperes into its resistor is R, or its resistance is R. The negative to positive, which is a plus, it is 165, which is equal to 0. If we are simplifying this further, it is if we are doing this particular calculation by using the calculator, this will be the minus 60. This will be the minus 90. This is minus 3R plus it is 165. If we are solving for the R, this 3R, which is equal to 165 minus it is 150. This is minus 150, which is equal to it is a 15. That's why R is equal to, here in this case, this R is equal to, it is 15 divided by 3, and its value is coming to be 5 ohm. And these are some methods to find out the value of the unknown depending on the requirement by using the basic laws, that is KVL and KCL. For this particular video, that is the stuff from my side. Thank you.